Good afternoon, everyone. This is Janice Connell, and this is my Lab 2 video. In Lab 2, we were to observe the motion of a falling object, use Tracker to gather the observational information, construct a computational model using Python to do two models. One using gravity as the only impacting force, and the second one to modeling gravity and drag as the impacting forces. We were to compare the two models' results to the observational results. This is my scenario here. My husband dropping a wadded up paper towel to the ground from a distance of about 6 feet. I gathered the tracker data here, and in this case I'm only interested in time over the y-axis. I put that information into my spreadsheet here, so I have time here and then my observed model here. Then I used Python to model Newton's second law, which says that the change in the momentum of the system is equal to the net force acting on the system times the duration of the interaction. The main thing I needed to figure out was what the net force was. In this case, Model 1, I'm only going to show the gravitational force. And the way I describe that in Python is a formula where W equals the mass of the ball negative times the gravitational constant times J hat. Gravitational constant is 9.8 meters per second squared. So I put that information from Python here, I modeled, and you can see my observed line, a position over time here in orange, and the modeled position over time in blue. Here the model is overestimating the position in time. So something is slowing the object down, and this case we know it's drag. I also looked at the velocity over time in this scenario, and you can see it's a straight line. Velocity is constantly increasing here per the gravity constant of 9.8 meters per second squared. In Model 2, I'm going to add in a drag force factor, so F sub D is going to be drag. And I defined that as B, which is a coefficient for drag, times the velocity of the ball squared. And the reason I did this is that there is a positive correlation between speed and the drag on an object. So the faster an object is going, the more drag is impacting that object. I also defined B to be 0.0027. I did that through experimentation as instructed in the course video. I plotted that information here, and these are the results of observed in orange and modeled in blue. You can see that although the lines are much closer, the model here underestimates the position over time. I feel that I need a better representation of drag. There's several things that impact drag, but the two biggest ones are the speed of the object and the cross-sectional area of the object. So if I could estimate the cross-sectional area of that object and add it into my model for drag, I think I would have a better representation. I also feel there might be a little video distortion going on. We were asked to look at velocity over time and whether or not the object reached terminal velocity. Here you can see that my velocity over time for Model 2 is not a straight line, it's a curved line, and as it flattens out here, it means that the object is approaching terminal velocity. In this actual observation, I did not reach terminal velocity. However, if I had dropped it from a greater height, I think we would have seen that, because the air resistance will ultimately overcome the force of gravity to offset each other. We were asked to look at two scenarios where a ball was thrown lightly instead of just dropped, and where a ball was thrown with greater force. I modeled those two scenarios in Python and came up with these two lines, positions over time. The top line is the ball that's lightly thrown, so you can see it has a little bit faster initial velocity, but it will reach terminal velocity given that it's falling from a big enough distance. For the object that's thrown hard instead of just dropped, you can see the velocity is much higher in the beginning, and then it slows down as the object will reach terminal velocity. And terminal velocity will be reached because of the positive relationship between drag and speed. Ultimately, that will overcome the force of gravity, and a constant acceleration will be reached. This concludes my video. I hope it was educational, and I look forward to your comments. Thank you.